Just kidding. Okay. Let me see. Okay. So you might be seeing now the slides that I just I shared. Here we are going to cover two topics. One is going to be linear momentum, and another one is going to be collision and impulse. So let me give you a little bit brief overview of these two topics, and then we go into the details of them. And I know these two topics are kind of challenging topics because it's a kind of new concepts for you. So at this point, we will kind of ramp up a little bit slow towards these topics, and then once we have a little bit background, then we can attempt some problems. So what is momentum? Momentum is all the objects that we see in this world, they are going with some velocity. And of course, they have some mass as well. So when you multiply the mass with the velocity, the quantity that you get, it is called linear momentum. Collision, it is normally in our everyday life, most of the time when there is a car accident, you call Najam, and then you are saying that there is a collision on the roadside. So collision is basically the interaction between the two bodies, like kind of you are seeing my hands and I'm hitting one hand with another hand. So this is called a collision. One object is hitting the other object. So it could be a stone hitting the road, or it could be a ball hitting the wall, or something other situation like that. It can arise, and that will be called collision. Impulse, it is also the during the collision, you see that why an accident is happening on the road, because one car supposedly is going in front that is kind of slow, and the next car is coming from behind and it is a little bit fast, and both of them are stubborn and changing the tricks, right? So the lowest, the car that is coming from behind, it is fast, so it will definitely hit the first car. So during that time, what a person can observe is that the car that was coming from behind, the speed of that is going to change. So we say the change in the velocity, like when the velocity is changing. So the change in velocity, we are calling it acceleration. And when you multiply the mass times acceleration, that will be force. So the force is applied during to the car changing the speed, okay? And also there is a time interval, because a collision is not happening like a fraction of a second. There is some time, like a fraction of a second or minute or whatever. It could be a seconds, but some time is involved, like a non-zero time is involved in that. And during that time, the force was applied. This product of the force times the time interval, that is called impulse. So let's try to understand the linear momentum here. For a single particle, we define a quantity called its linear momentum, which is as I mentioned, it is called the product of mass times the velocity. Mass is, of course, the mass of the particle and velocity at which it was going. So for the sake of this discussion, to carry on from now on, what we will be doing is we used to consider the constant mass of the object. Like this is the marker, and the marker having a constant mass. It is not changing with respect to a time for the time being, right? So this is a constant mass. But if as compared to this, if I was holding a stick of ice, then we will see that the ice will be melting, the water will be dripping out of it. So during that time, the ice mass is changing. So we are not considering that situation. All the situation we will be considering, it will be like kind of this marker, which will not be changing with respect to the time. So the mass is constant quantity in our situations. The only thing that is going to be changing, that is the velocity, okay? So suppose I say the momentum is the mass times velocity, and you know that here on right side, the mass is scalar quantity, the velocity is a vector quantity. When you multiply scalar with the vector quantity, you get a vector. Therefore, the momentum is also a vector quantity. Can someone tell me what will be the unit of the momentum? Yes. Please answer.
Kilogram meters per second square.
Yeah, kilogram meter per second. Kilogram is the unit of mass. The meter per second is the unit of velocity. So that's the kilogram meter per second is going to be the unit of linear momentum. Okay. Now, as I mentioned that in this situation, when we are observing any particle, the mass of that is not changing. The quantity possibly can change, that is the velocity. So if I take the time derivative of the momentum with respect to time, you will be seeing that the mass is constant. I took it out, and then I took the derivative applied the derivative on the velocity. So what does this quantity represent?
Acceleration.
It is the acceleration, and it is called instantaneous acceleration. So we know that the mass times acceleration by Newton's second law, it is equal to the force. So we say that the force is actually can be seen by the change in momentum with respect to time. For example, the car was initially coming with 100 meters per second initially, and afterward it come to a stop. So there is a change in the momentum, mass of the car times 100 meters per second, that was initial speed, and 0 times mass. The 0 is the final speed times mass, which is 0. So there is a change in the momentum of the car, which is equivalent to the force applied to the next thing. With it, the car was interacting. Okay. So this is the Newton's second law, can be expressed in terms of the momentum. Now I'm going to give you a little bit example of some tennis balls. So suppose that I'm having a situation like you have this bag of the crate of tennis balls, and it is having lots of tennis balls. Okay, like 9 tennis balls are there in this box. A friend is asking you to throw it to the right side with some velocity. Okay, so it was completely packed and you've thrown it in one direction with some velocity. And suppose this velocity, the direction in which you have thrown it, is the plus x direction. So since this is a completely packed mass, okay, so the center of mass, we know it is going to be kind of geometrical center of that. The velocity at which it is going, what will be the name of that velocity? Velocity of center of mass. Okay, so this velocity is equal to the velocity of the center of mass at which it was going.
From the center?
Yeah, because the total, now you should be considering the entire system consists of 9 tennis balls.
Yes.
So it's not a single tennis ball, but 9 tennis balls in the box. And suppose ignore the mass of the tennis ball, the crate. All you are seeing is
I must
9.
consider it as one object or one system.
Exactly. Currently, we are considering it as a one system. It is completely packed, not moving at all. Everything at rest with respect to each other. Just the total system means the 9 balls are going in that direction. That's all we're considering now. So the center of mass is here, and the velocity at which it is going to the right side, this is called the velocity of center of mass of the object. So when the object is coming from position 1 to position 2, suddenly something happened and the entire box just exploded somehow. Okay, so some balls are going in this direction, other balls are going in that direction, something like that. Okay, something like that is happening. You see the initial space between them was small. Later on, the space between them becomes larger. Normal observation is that when we see this kind of object, when it explodes, it still keep going in the same direction, even though the distance between the balls is kind of increasing, but the net moment of all of the objects is still in the right direction. So if there was no air resistance, nothing like that, what we will be seeing is that the object speed afterward will be the sum of all speeds. So this is particle 1, speed 1, particle 2, speed 2, particle 3, speed 3, and so on. Okay, so on like that. You can assign the nine numbers to it. So every ball is going to be going in its own direction, like some up and some down and some just completely straightward. But when you add all of the velocities, all 9 velocities, when you add all 9 velocities, what you will get is that the net velocity is going to be exactly like this much. So suppose this one had a mass, capital mass M, and velocity center of mass. So we call this as the momentum of the center of mass of the particle. Now afterward, when I'm looking at this total momentum afterward, means the final momentum, I'm seeing that suppose all the balls are weighing the same, so assign M to them, but then every one of them is going with a different speed, so velocity, so V2, V3, and so on up to V9. Okay? But if there was no air resistance, nothing like that, no extra forces acting on it, so what we will see is that the initial moment of the center of mass, initial, will be equal to the final momentum of the center of mass. Both of them are going to be the same because the net motion of the particles is still going to be in this direction, like kind of conical shape like that. And then the x components will completely cancel each other. Only the y components will cancel each other. Only the x components will remain, and that will be exactly equal to the v center of mass. And I'm explaining this concept a little better in the next slides. But for now, what you are going to understand is that if the system of particle was coming with some speed and somehow it got exploded, each particle can have different velocity, but when you add all the velocities of them, or for general words, for general sake of the generalization, you say we add the momentum of all of the particles, it will be exactly the same, the initial momentum at which the particle was coming in. Okay? So, before going into that, now I want to emphasize this, that here you see this force, which is equal to the change in momentum versus time. And we also know that when we are talking about the force, means the mass times acceleration, and the acceleration is the change in velocity over time. Okay, so now I'm going to solve this problem, the next checkpoint, based on this concept. Here we have the checkpoint 3, and the figure gives the momentum B of the linear momentum versus time for a particle moving along an x-axis. A force directed along the axis acts on the particle. Rank the 4 regions indicated according to the magnitude of the force, greatest first. Okay, then first let's do this, the part number 1 and then go to the part number 2. Looking at this figure, 4 regions are identified by 1, 2, and 3, and 4. Just unmute yourself and you can answer these questions. In region number 1, when you are determining the momentum, so momentum is on the y-axis and the time is on x-axis. So when you are looking for the change in momentum with respect to the time, which is basically delta P divided by delta T, will you find out delta P by delta T positive in region 1 or negative?
Positive.
Positive.
Positive. And how about that in region 3?
Negative.
Negative. Okay, and then when you compare region 1 with region 2, in which one you look at the slope look to you more?
3. Magnitude is bigger, maybe.
Don't you see
number
that?
one is bigger because the slope is farther.
1, yeah, sharp.
Okay. The slope is sharp, so therefore the slope in the region 1 is large. The force will be applied in their region more as compared to 3. And we are not concerned about the positive sign and negative sign because they are asking for the magnitude. Is more than as compared to region number 3.
And 2, 4 is 0, right?
2 and 4, the slopes are 0 because the momentum is constant. So the constant divided by time is going to be 0. Or you can say the derivative of the P for the constant region is going to be 0. So when we are going to rank them according to the magnitude, what we will see is that the force in region 1 is greater than region 2, greater than the region 2 plus equal to region 4, right? Something like that. In the second part, the answer is displayed now, but in the second part, when they say in which region is the particle slowing, we can see that as you were already telling me that the region 1, the graph is positive slope, and the region 2, region 3, the graph has a negative slope. So the negative slope means negative force, okay? And in that region, the particle has negative acceleration, which is deceleration, and the particle is slowing down. Okay, so that's been established. We will be keep using the momentum concepts now along with the collision and the impulse. So the collision, as I have mentioned, that the collision, as we normally understand, it is normally the collision between two cars that we use in our everyday life. But the collision is basically between every other surface. Like you are putting your laptop on top of the table, so the laptop is colliding with the surface of the table. Or you are sitting in the chair, so you are colliding with the chair. Something like that. All these things, when the two objects are interacting with each other, there is a collision happening. What is collision and what it does? So you see that if I start to throw this marker towards this whiteboard, what will happen that you can see that the marker will initially go and it will hit the surface of the whiteboard. If it was some inclined, then it will kind of become parallel or something like that. And then if it was a little bit elastic, then it can also bounce. Okay. So that is what happened, that initially the direction of the motion of the marker was this way. What the whiteboard did, it stopped this particle, which is the marker, and then it is trying to change the direction of the motion of this marker, either downward, upward, or completely bouncing it back. So these are the scenarios which happens between the collisions. Suppose the two cars are coming, like the car number 1 is chasing a car number 2. Both of them are hitting, like the back car is hitting the front one. So this car was initially fast. It will slow down to the speed of the first car, or if it was stopped, then this will also become stopped. Okay, and suppose there is not huge damages happening, so this car can bounce if it was like plastic type, like as we are seeing the tennis ball. But if it was made of the metal, then most of the cases we are seeing that the car go a little bit shrink, like kind of a sponge type shape, like kind of shrink from the hood type. Okay, so let me explain this situation in terms of the Newton laws and the action and reaction. In this figure, what you are seeing, a ball is coming along x-axis, but the ball was initially going towards negative x-axis. The ball is hit by the bait, so it is trying to slow down initially, completely come to a stop, and then the ball bounce back and go in the backward direction in the negative x-axis. Okay, So during that collision, there is an action and reaction happening. One force, there is a single force, the object that we consider it is the ball. So the ball is applying one kind of force, and there is another force, reaction force, on the ball, which is moving the object to the left direction. So two things are happening. If you look at the, consider the entire scenario. First is the force, and second is the time. Because the ball took some time while interacting with the bait. And during that time, if you clearly look at this, the force is not constant. Why it is not constant? Look again at this, my hand here. Suppose this is the ball as it is coming towards the surface. What will happen that as the ball is approaching to the surface, it will initially touch the periphery, outer periphery of that, and then the ball will kind of deform a little bit, this front, right? And after that, once it deforms, then it will bounce back. So during the entire course of that time, the force was not constant. So we cannot sometime explain the scenario using the constant force concepts. There could be very variable forces acting on that. But what we can do is that we can generalize the situation and use the average force instead. So what you see is, we already know that the force is equal to change in momentum with respect to time. So if I know that the force is not a constant force, it is a variable force, then I need to apply the integration in order to determine the change in momentum in that scenario. So the people who are using the integration, they multiply first with the delta t both sides and then take the integration. Okay? So delta p is going to change from the initial momentum to the final momentum. And then we also see that this force is a time-dependent force, while it was applied in the interval from Ti to Tf. What you see on the left side, the d and the derivative, both are, the integration cancels, and what we're left with is the Pf minus Pi, which is equal to delta P. Okay, we know on the left side we got delta P. On the right side, look at this quantity. Under the integration sign, the variable force times delta T. This quantity has a name, and the name of that is impulse. We represent that by J. Okay? So the impulse is equal to change in momentum. If it was along x-axis, we also say along x-axis. If it was along y-axis, we also say along y-axis. Okay? So the change in momentum, supposedly, if the particle was coming along x-axis and then it returned back along x-axis, then the total change in momentum happened only along x-axis. So therefore, the impulse will be along x-axis as well. If the change in momentum happened along y-axis, then the impulse will be also along y-axis. Okay, there is another scenario, and let me give you that example. Suppose that you went to a pool for swimming, and sometimes one friend is teasing another friend, and he is pushing that friend to the water. What he's doing, that he is coming from behind, and he is pushing the person with his hand. But if you look at the slow motion camera, supposedly, what you will be seeing that the person A, like the friend who is pushing the other one, he is approaching to this person and touching just barely his back with the hands, like this, right? And then as he is coming close to it, his hand will be deforming like that, and entire palm will be touching his back now, like this kind of such a scenario. And then the person who was coming from behind, he had some momentum. That momentum will be transferred in this collision, and the person who he was pushing to the water, he will be losing the balance and will eventually get into the water. So during that time, if you look at that, the force was again not constant, and the person, this collision which happened, it happened during some time, from the TI to the TF. Again, this is called impulse, and that impulse has happened, which was the change in momentum of the person who was standing right there. Because the person who was standing next to the water, he was initially at rest, suppose, later on he gets some speed and he gets into the water. Okay, so there is a change in momentum and collision has happened here. So the impulse and the linear momentum theory, I already explained here, but let me build up on this concept right here. Before going into it, let me ask one question from you. You are driving your car, right? Please answer this. Why your cars, even though these are very good luxurious cars and very well maintained cars, why do they have plastic bumper as compared to a steel bumper?
Can you repeat the question? Your voice was lagging.
Okay. So you have this, you have cars, right?
Okay.
And the cars are having plastic bumpers. They are made of polymers.
Yeah.
I said, why your car is not having bumper that is made of steel instead of polymer?
Because it's lighter.
Answer is
Because
here.
they're still heavy.
The answer is here.
Because
You are
It's
engineer.
better at absorbing collisions, so it's less likely to deform.
It is it is more likely to deform because it is polymer compared to a steel. Okay. The answer is here. The answer is that we are calling this area under the curve, right? This integration is the area under the curve. So when your car is having the bumper that is made of the polymer, what happens then? The car, during that collision, it takes some time to completely deform.
so the area will be bigger.
So the impact, yeah, so the impact of the force from the collision will not be directly transferred to the passenger as well as the driver. So the time interval right here is increased while the force is decreased. If it was made of steel, what happens then? The time interval is short because the shock from the collision will be directly translated to the passenger as well as the driver, which is lethal. And in that time, the force applied will be high because the change in momentum is happening. Suppose initially the car was coming with 100 meters per second and later on it is at stop. So the change in momentum is not changing. The impulse is not changing. The impulse is the area under the curve. It is now your choice either to make this force high or just take this, increase the time interval. So if you increase the time interval, this force will be decreased and the area under the curve will remain the same, like as you are seeing on this slide, slide number 1 and slide number 2. If you use a bumper like that is made of the steel, then the scenario will be most likely to be the situation 1, like figure A. And if you made the plastic bumper, the situation will be more like situation B. In the situation B, you see that the time interval is a little bit large and the force peak has been dramatically reduced. So that will be the scenario, okay? If you look at the old cars, some of them are still running on the roads, you might be seeing A lot of old cars, they have the bumpers that are made of the steel or the iron, right? And that was basically the drawback in the old technology. The new technology completely transfers towards these bulky bumpers, which are made of the polymer.
So it's
Okay.
for safety purposes, right?
It is for the safety reason, yeah, because you either increase the time interval or the force. So in the old cars, the scenario will be large amount of force will be transferred to the passenger and the driver. In the new technology, the time interval is large, so less force will be transferred to the passenger and the driver. So there is a little bit more safety for the passenger and the driver. Okay, this is an example that will be explaining the situation that what we just discussed. A paratrooper whose chute fails to open, land in snow. He is hurt slightly. Had he landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. Does the presence of the snow increase, decrease, or leave unchanged the value of the paratrooper's change in momentum? What do you think, guys? Is the momentum changing here?
Do they mean the instantaneous or the overall?
He is coming, like if he's coming kind of diving from the sky, then he has some speed before touching the snow, right? Some speed. Accordingly, he had some momentum. So that speed and that momentum does not depend whether he is landing on the bare ground or in the snow. That momentum will be the same. And as well as the end momentum is also the same, because if he landed on the snow, eventually he came to a rest, momentum is zero. Or if he was landing on the ground, he also came to the rest and the momentum is zero. So the change in momentum is not there. It's not changing. So the change in momentum will remain the same, either in the snow or in the bare ground. Like, let me give you this one example. Probably it will remove a lot of doubts. If you were about to jump from your roof, okay, for some reason, for enjoyment, will you prefer to jump to the bare ground or to be lots of foams put in front of you and then you are jumping to the foam? Will you prefer jumping to the foam or to the bare ground?
Foam.
Why?
Aren't they the same?
So, no, like why you will prefer to jump to the foam is compared to the bare ground?
Not to damage myself or hurt myself.
Exactly, this is the thing. What you are trying to do is to foam, since you are hitting the foam, there is a lot of time for you to get into the lowest point. So your momentum is changing during a lot of time. That's why you are reducing the force while increasing the time interval in the foam. But if you are getting into the ground is not elastic. You are just hitting the ground right away, so all of your momentum is changing in a very short interval of time. Therefore, this force will be extremely high. And that's why it is lethal and dangerous to jump into the bare ground versus jumping into the foam in that scenario. Okay? The same is the impulse stopping the paratrooper, will that change or remain the same?
Well, since the impulse is net change, it will not change. So it's the
Yes.
final minus the initial, it will not change.
Exactly. So for the part A and part B, both of them are unchanged. What about the force?
The instantaneous force will change, will be less.
It will be less because the time interval is large, so therefore the force will be less. Okay. Okay. So now, at this point, what I'm considering is that you at least understand the concept of momentum. You also understand the change in momentum. and the change in momentum is equal to the impulse. These things are understood now for a single object. Now let's talk about more objects, more than one object, which will be the system of particles. So in this diagram, what you are seeing, that there are n number of particles, they are fired towards a target. Okay, so each projectile, suppose all projectiles have the same mass initially, they're hitting the target and they're bouncing back. So during that time, some change in momentum for the particle 1, 2, 3, 4, and all particles eventually has happened. So if I consider that the change in momentum for the particle 1 is equal to Pf minus Pi, right? Since all particles are coming with the same speed and they have the same initial velocity as well as final velocity, so if I had fired 10 particles, then all it is going to be is I will have 10 times delta P equal to 10 times of the change in the momentum of a single particle. That's all will be happening. Okay. So suppose that I have fired n number of particles. So the total change in momentum is going to be n times delta P. Okay. Since we know that this is going to be the impulse because J is equal to delta P, for the n number of particles, the J is this because the change in momentum times the n number of particles, which you can also express as n times J1, if you want to express it that way. Okay, the impulse of the particle 1 times the total number of particles, it is giving me the total impulse. This is the equation. Now I'm interested to know how much force has been transferred to the projectile or to the target, because both of them are exchanging the forces right there when they interact. So during that time, if I say that the force is equal to delta J over delta T, because the change in momentum is happening because of that. Or if you are not familiar with the delta J, you can just say J, if that what suits you. J over the interval of time. And I'm going to put here, but just now I'm putting the n negative sign delta P with delta T. Why I put the negative sign? Just look at on this slide. There are two objects. One is the projectile, another one is the target. The projectile is transferring the impulse to the target. The target is transferring the impulse to the projectile. So if I'm saying the resulting impulse of the target on the projectile, I say n delta P. So one is transferring on the side, another one is transferring on the negative side. So obviously, J is a vector quantity. So for one, it is going to be positive. For another one, it is going to be negative. So that's why the negative sign has appeared here. Okay. So when we are looking for the total force applied,
the momentum is conservation of momentum.
Yeah, conservation of momentum. I'm implying that kind of concepts now, but I'm not explicitly saying it. Okay. Conservation of momentum will be the next topic. Hopefully, we will be covering that tomorrow. Okay. Oh. Yeah, but explicit, yeah. If you are familiar with that concept, yes, there is a conservation of momentum is there. Yes. Okay. So the force, the average force is equal to n delta P divided by delta T. This delta P here, what we know is that the momentum delta P, as I mentioned before, the mass is not changing, only the change is happening in the velocity divided by delta T. Okay. This is my general equation. I'm really happy to leave it here without any further modification of this equation because it has a lot of information and I like to keep it like this. But sometimes the situation will be like this. Suppose you are holding the sands in your hand and you are having a plate here. and sand is going from your hand towards that plate. So each grain of sand is transferring some momentum to the plate, okay? But you cannot really count sand particle number 1, sand particle number 2, because it's lots of them. So in that scenario, instead of saying a discrete number, you will be happy to discuss that out of 1 kilogram of sand particles, 5 gram or 50 gram just hits the plate. Now 100 grams has hit the plate. So you will be more happy to explain that situation in terms of the fraction of mass rather than just saying grain number 1 change the momentum delta P. So in that situation, if it arises, that this N delta M will be expressed as change in mass rather than discrete term here. N delta M is more suitable for the tennis ball situation in which you can count 1, 2, 3, 4. Delta M is more suitable for the situation in which you cannot easily count the particles, like the situation of the sand. Okay, so then you are expressing this delta M V divided by delta T. And then as you are holding the sands and the sands are going downward, so the mass approaching to the plate will be the function of time. The more time passes, the more sand will reach to the surface. And that's why you have delta M by delta T, you can express in that way. So that will be later on some situation we'll get into that and we will be discussing. It is also the principle behind the rocket. Like you are seeing the rocket as they are fired, there are lots of gases in the rocket. It is burning that fuel. So the mass of the rocket will be reducing with the time because the fuel is consumed. The same is in your car. You fill the fuel in your car, it is completely full tank. As you are driving the car, you are continuously consuming the fuel. So with the passage of time, the mass of your car will be decreasing because the fuel is going out of it. Okay, let's do this checkpoint. It is a kind of general topic. It will cover a lot of things. The figure shows an overhead view of a ball bouncing from a vertical wall without any change in its speed. Consider the change delta P in the ball's linear momentum. Is delta Px positive, negative, or 0? And then delta Py positive, negative, or 0? And then what is the direction of delta P? So as I mentioned before, that whenever you see this kind of language, an overhead view will be such that, for example, something is happening, like I'm throwing this duster to hit, and then it is going outward, and someone is from the top looking at it. So that will be an overhead view. Side view or the cross-sectional view will be such that something is happening and you are in the plane of the object, you are looking at it from the parallel perspective. So overhead view, when they say it eliminates a lot of forces for us. One of them is gravity, like that. Okay. So in this, answer part number A. Is delta Px positive, negative, or 0 in this case?
It's positive.
Is it positive?
0.
Okay. 0. Yes, it is 0. And the reason is here. You see that when the ball is coming down, we know the momentum direction is down. I put the two components of that. One is the y-axis, another one is the x-axis. So you see the x-axis to the right side. When the object goes upward, it is again a vector quantity and resolve this in components. And you see the x component that is to the positive x-axis. Okay. So when you subtract the initial the initial from the final, what you will get is 0 because it is mvx. Both of them are the same, which will cancel out. But on the other hand, if you look at the y component of the momentum, initially it is downward, later on it is upward. So the main difference is the sign. The mv remains the same, but the sign is different. Okay, because initially downward, later on upward. When you subtract these two, then you will get another quantity which will be a non-zero quantity, like is shown in this figure here. When they are asked for the last case, what is the direction of the delta P? Since we know that delta Px is 0, the sense of direction in this delta P will survive just from the delta Py. So delta Py is obviously to the positive y-axis. Therefore, the total momentum direction will be also to the positive y-axis. Okay. Do you have any question here?
It's clear.
Okay. Okay, guys, just raise your hands now, and this is the end of our class today. Okay. Al-Jasam Alawi, Ammar Abdul Rahman, Hamza Abdullah, and Hamza Abdul Hamid, and Tamam Said. Okay. Okay, so the class is over. You can leave now. Just enjoy the couple of minutes. If you have any questions, you can stay with me for your questions.
Thank you, Doctor.
Yeah, no problem. Yeah.
Thank you, Doctor. Can we leave?
Yes, yes.
Okay, thank you.
Doctor,
Yes, doctor.